Functions. A function is a number machine that transforms numbers from one set, called a domain, into a set of new numbers. The set of transformed numbers is called the range of the function. A function is a consistent machine in the sense that it always transforms a given domain number into the same range number. Sometimes we call a number from the domain the input of the function, and the number that comes out is the output of that function. When using x and y, it's customary to let x represent the input number and y the output number. We also call x the independent variable and y the dependent variable. Some keys on your calculator are function keys. For example, the square root key is a function key, and it has as its domain the set of non-negative numbers. A precise definition of function in mathematics is: a function is a set of ordered pairs, no two of which have the same first component. The domain is the set of first components, and the range is the set of second components. For example, the following is a function. But this one is not. Because 9 produces two different numbers, 13 and 11. The domain of f is the set of first components, or 2, 4, 5, 7, and 9. And its range is the set of second components, which are 3, 6, 10, and 13. This definition here is a table definition. In the previous example, f was represented by a set of ordered pairs, but we can represent it as a table of inputs and outputs. In other words, the ordered pairs are 2, 3, 4, 6, 5, 3, 7, 10, and 9, 13. Functions are named by letters, usually starting with little f or big F. If the name is little f, then the function notation f parentheses x represents the output when the input is x. In the above function, f of 9 is equal to 13. This means the function transforms the input number 9 into the output number 13. There are 4 ways to represent a function: by a table or set of ordered pairs, by a description in words, by a graph, or by a formula. Here are some examples of ways 2 through 4. Here's a function defined in words. Its domain is the set of positive integers, and the output is the sum of the factors of x. That is, for any positive integer x, f of x is equal to the sum of the factors of x. Here are some examples. F of 9 is the sum of the factors of 9. 1, 3, and 9 are the factors of 9, and they add up to 13. F of 12 is the sum of the factors of 12. Let's see, 1 goes into 12, 2 goes into 12, 3 into 12, 4 into 12, 6 and 12 all go into 12, and they add up to 28. Here's a function where the domain and range are the numbers between -2 and 3, and the function is defined by a graph. F of -2 can be found on the graph. You look for x equals -2, go up to the graph, and determine the y value, which is 1. F of -1, find -1 on the x-axis, go up to the graph, and read the y value, which is 3. F of 0, when x is 0, you go up to the y value, that's the y-intercept there, and that's 1. F of 1, find 1 on the graph, the x value, go to the graph, and read the y value, which is -2. F of 2, well, that's right on the x-axis, and the y value is 0. That's an x-intercept. Here we have a function defined by a formula, and the domain is all real numbers. F of 9, you merely substitute 9 for x and work it out. F of 9 is 13. F of 12, substitute 12 for x and work it out, and you get 19. The formula way of defining a function involves substitution. A variable, which is usually x, is needed to define the function, and this variable should be thought of as a placeholder or a box. For example, the definition f of x equals 2x minus 5 has the meaning f of box equals 2 times box minus 5. When we put a number in the box, we follow through consistently. So if we put 9 in the box, we follow through, and we get f of 9 equals 2 times 9 minus 5. The variable need not be x. If we use w instead, then f of w is 2 times w minus 5, and if we use an expression like 7x minus 3, then f of 7x minus 3 is twice 7x minus 3 minus 5, which simplifies to 14x minus 11. When there are two functions, this rule of substitution, putting something in the box, gives us what is called composition of functions. If the functions are f and g, then the composition f parentheses g parentheses x parentheses parentheses represents the function you get when you put g of x in the box of f of x. That is, you first compute g of x and then use that as the value of w to compute f of w. And the composition g parentheses f parentheses x represents the composition that you get when you put f in the box of g. Let's look at an example. Suppose f is defined by the graph shown here, and g is defined by the formula g of x equals square root of x squared minus 2x plus 1. Let's find f of g of negative 1. We start with g of negative 1, and that's the square root of negative 1 squared minus 2 times negative 1 plus 1, which is square root of 4, or 2. So we have f of 2, and we look at the graph and find 2 on the x-axis, and the y value there is 0. So f of 2 is 0. Now let's find g of f of negative 1. We start with negative 1 on the x-axis to find f of negative 1, and look at the point corresponding to that. So we have g of 3. And we put that in the formula, which gives us square root of 3 squared minus 2 times 3 plus 1, which is square root of 4, or 2. When a function is defined by a formula and the domain is not specified, then it is assumed that the domain is all real numbers for which the function makes sense. That is, the formula can be used to produce a real number. In this lesson, we are assuming that we're dealing only with real numbers, not imaginary numbers. For example, the domain of the square root function is all non-negative real numbers because you cannot get a real number by square rooting a negative number. For example, the square root of negative 9 is not negative 3 because negative 3 times negative 3 is positive 9. If we use imaginary numbers, we could call it 3i, but we're not going to use imaginary numbers at this point. So when you have a square root function, the domain must exclude any numbers that produce a negative inside the square root. Let's look at an example of this. If f of x is the square root of x minus 5, then the domain of f is the set of real numbers greater than or equal to 5. We write it this way. The left bracket and the right bracket mean set of, and it tells us we're talking about an x. The vertical line means such that, and then we have the condition written as x is greater than or equal to 5. If the function contains x in the denominator of a fraction, then the domain must exclude any numbers that make the denominator 0. Here are some examples. F of x is x minus 2 over x minus 3 plus x over x plus 5. The domain is all numbers except 3 and negative 5. G of x is square root of x minus 2 over x minus 5. The domain is numbers greater than or equal to 2, so that you don't get a square root of a negative, and excluding 5, so the denominator is not 0. And so we come to the end of this lesson.